Nguyen, you can start.
Oh yeah, all right. I will start my presentation now. Um, so hello everyone. My name is Ronan Khac-Duy Nguyen. I just like to briefly introduce myself. I am, for some of you, I have been involved in some activity of ANSHM, but this is the first time I participate in the ANSHM workshop. So I got my PhD degree from QUT 2 years ago with Professor Tommy Chan and has been working with him as the research fellows since my graduations. So firstly, the research on system development is one of our priority at QUT to bring structural modeling technologies to be more practical and closer to real-world applications. And as you can see, here we have a building, we have a complex, we call it a P-block or a QUT Science and Engineering Centers, which has achieved a 5-star green rating from the Green Building Australia. And we have installed an ANSHM system on this building with 3 subsystems. The first one is vibration system with accelerometers. The second one is the structural performance system with strength gauge. And the third one is subsurface monitoring system with acoustic emission sensors. So in this slide, you can see the diagram of the monitoring system. The sensor actually is installed on different floor of the building to measure the vibration response and acoustic emission response. Although you can see here it's kind of a cabling system, but the way it works is very similar as a wireless system because at its sensor, we have a DAQ node. Okay, and we manage the system through the IP addresses of the DAQ nodes. And using this Ethernet-based system, we significantly reduce the amount of cables, and we can utilize the existing internet facility of the building and making the system, the ANSHM system, compact, stable, and cost-effective. And later, I will show you how we utilize the data we acquire from this monitoring system. In this slide, I would like to show you some developments on sensors and measurement devices. Fiber optic sensors, such as FPG sensors, are normally used to measure strength, right? But we developed 2 methodologies to measure displacement using FPG sensors. In the first approach here, we use 2 pairs of FPG sensor array, one in the top and one in the bottom of the beam, all right? So to measure the curvatures, and later on we use it to estimate the displacement, the vertical displacement. In the second approach, we measure the slope using 5 FPG tube sensors, and we use the data to estimate the displacement from the slope. And the both methods show accurate results compared with the direct measurement. These 2 methods is very convenient compared to traditional methods because we don't really need a reference, and it makes the methods to be more practical in real world applications. In another study of FPG sensors, we developed an actual accelerometers using FPG sensors based on the principles of transverse force of string. As you can see here, we have a mass at point C. When this mass is moving up and down, it's because the change in the length of the string. And if we can measure these changes using FPG sensors, we can estimate the accelerations. And by combining this principle of transverse force with the principle of axial force here, we also develop a biaxial accelerometers using dual FPG sensors. Under applications, we develop some methods for structural condition assessment, such as the correlation method or the activity artificial neural network methods or the multi-criteria approach. And I will go into detail here. The first damage identification methods I would like to show you today is actually a study of myself in my PhD's program. So in this study, we develop a method that work for complex structures. You can see here we have a very complex trust bridge with a lot of members. So we try to develop a method that work with high uncertainties in the identification of structural parameters. So we found that the change in modal strength energies agent value ratio, we call it MSEE, can be estimated from the measure frequency and mode set. So this parameter is little affected by the numerical model. And to identify the damage features, we use genetic algorithm to optimize the correlation level between the measure MSEE chain and the analytical MSEE chain. Here you can see some experimental results. As you can see from the left figures here, we have very similar natural frequencies between the experimental models and the epi models with the errors of about up to 2% in the frequency. Also, if you take a look at the MOSEP, they look very similar, but actually they have big differences. If you look at the MAC value, the highest MAC value is only 0.653. All right. And normally, if we want to use this FEM model for damage detections, we need to calibrate it. We need to update the models. And this is very challenging work to update a model with this value. All right. However, the models, the MSEE methods developed in this study can still identify the damage quite well. It can well identify the single damage as well as with the increasement of damage on that locations. Also, it can identify double damage as well. You can see here, two damage at number 7 and 67 can be identified quite well. Here we have another damage identifications in which we apply artificial neural networks and modal strength energies to identify the damage on slab on girder bridges. And as you can see in these graphs, the modal strength energies index had a clear pattern due to the location and the severity of the damage. Therefore, we use modal strength energies damage index as the input to the ANN, and the output will be the location and severity of the damage. And we achieve accurate result with this approach, which has not been shown here, but we have published some paper on this. Another development is the multi-criteria approach for asymmetric building. So an asymmetric building can be defined as a building with eccentricity in either geometry or the mass parameter of the structures. So such buildings exhibit complex vibration, such as a coupling between the lateral and torsional component of vibrations. And because of this complexity, single criteria approaches may not work. So we develop a multi-criteria approach based on modal flexibility, based on modal strength energies for lateral MOSEP component, and modal strength energies for vertical vibration components. And you can see here, we could see that the big improvement of the proposed methods when it can identify the damage location very well without any noise, while the traditional method failed to locate the damage locations. This slide shows another study on damage detections using static deflections. Okay, so in this project, the change in deflection DC at location X has been derived as a function of the damage location factor and damage severity. All right, and if you have a look at this graph, which is the diagram of deflection chain, we can identify the location of damage by looking at the nonlinear regions of the graph. So from the damage location we can inversely identify the damage severities from these two equations. And the experimental verification on beam structures here show very good prediction on the locations as well as the severities of the damage, which is 9.19% compared to 10.41% and 22.33% compared to 20.71%. This slide shows damage detection methods for arch bridges using modified modal flexibility index and modified modal strain energy index. So the indexes are based on the separation of the moss shape in vertical directions and horizontal directions. And then we take the higher index for the vertical and horizontal moss shape. And you can see here we have some result on arch bridge. We can clearly see that the modified flexibility index as well as the modified modal strength energy can identify very well the locations of damage in arch bridge. So apart from the research on structure condition assessment, our group also conduct research on performance monitoring, such as the study on stress fault identifications, load carrying capacity assessment, finite model updating, and deterioration assessment. So regard studies in pre-stress force identifications, our group has developed 3 different approaches. The first approach is called synergic identifications because it can identify at the same time the moving force and the pre-stress force. So as you can see in these equations, the displacement can be formulated as a function of moving force coefficient as well as a function of pseudo loss coefficient which relates to the pre-stress force. So by inverse calculations, all right, we measure the displacement and do the inverse calculation, we can identify the moving force and the pre-stress force. The result, experimental results, show here a good prediction of pre-stress force as well as a well matching of moving force. The second method is based on the simplification of the box girder bridge by a top plate. So instead of modeling a box girder bridge, we only model the top plate of the box girder bridge. And this study used neighbor methods and characteristic orthogonal polynomials to generate characteristic set function of blast with complex boundary condition, and then use inverse calculations to identify pre-stress force from measure displacement and acceleration response. And you can see here the prediction is quite accurate compared to actual pre-stress force. We have 2 different pre-stress force level here, and we could successfully identify the level of pre-stress force. The third approach is actually based on non-destructive testing using ultrasonic wave. And you can see in the left figure here, in the top left figure here, we have a transmitters and the receivers attack on the surface of the concrete. And you can see that the ultrasonic wave at different pre-stress force. And based on this, we do linear regression analysis to formulate the relationship between the pre-stress force and the velocity of the wave. And we can see it had a kind of linear relationship. So we can use this analysis to inversely identify the level of pre-stress force based on the wave velocity. We also conducted research on load carrying capacity assessment using ANSHM techniques. And in this project, vertical load testing is proposed to identify the load carrying capacity ratio. As you can see in this slide, instead of using a destructive testing to find the loading capacity of the bridge, we instead of finite element models that can represent nonlinear behaviors due to damage. Okay, so as you can see in this graph, the left graph, the load deflection diagram of the FEM, the finite element models, match very well with experimental results. And then this virtual testing approach can be used to estimate the vertical deflections as well as the bending stress at different states, at different condition, at different health state of the structures, such as the as desired condition and as is condition. Here in this slide, we have a study on hybrid automatic mode of dating. The conventional mode of dating has there is no meaningful way to consider the uncertainty in the test data and different confidence levels in turning parameters in the finite element models. So we may not have a reliable finite element models after updating. To address this deficiency, a hybrid mode of dating technique has been used here. In the hybrid mode of dating, uncertainty in the test data has been included by means of statistical scatters using the data over a period of time, and the confidence levels by interning parameters has been considered by engineering judgment. So we may have a more reliable calibrated model at the end. So you can see here we have some comparison result. The table shows the hybrid mode of dating provide a more representative updated model of the actual structures. For example, if you look at the first frequency, the errors of the proposed methods is only 1.83%, while the conventional methods had the error of 4.62%, which is a very good improvement of the hybrid methods. So that is the model updating of the structures at a particular period of time. So as a structural engineer, one question may be raised, may come to us. Can we assess structural deteriorations process in the beam marked here using vibration characteristic? So over the time, actually deterioration will reduce the performance of the structures as shown in this graph. So if we don't do maintenance in time, the deterioration can generate significant damage, which require much more money, with more budget to recover. So structural deterioration assessment is also very important apart from damage detection. So our group has developed a method based on time series analysis. The main developments include the use of low pass filters to cope with high frequency contents, and also the development of optimum model orders to balance between the model fits and model complexity. Also, we develop an index to detect deteriorations and employ Fisher criteria to locate deteriorations locations. We apply this approach to the B block building, which has been presented in my previous slide, using the data over 3 years from 2014 to 2017, and we can see the deterioration levels increase every year at every floor, at floors 3, 5, 7, and 9. Despite that, we haven't correlated the deterioration severity index with the actual deterioration actions occur in the building. So we expect by using ANN in futures, we can have more meaningful results. Previously, I saw a study on hybrid model updating, but that is a deterministic study. Deterministic techniques rarely provide a good correlation with real data due to the structure's complexity and inherent uncertainties. So therefore, in most cases, probabilistic approaches are more reasonable. Here we develop a probabilistic model updating approach using modular Bayesian approach. One benefit of this approach is that it's considered uncertainty thoroughly in the simulated model as well in the measured data. Also, the method is found more computationally effective compared with the fully Bayesian approach, but still at the same time can provide accurate results. As you can see here, the level of errors in natural frequency reduced significantly after we apply this technique. And we also use the updated model for performance assessment using reliability analysis. As you can see here, we calculated the reliability index for the strand and deflections. And for the damaged structures, for the damaged box girders, we see a significant reductions on reliability index. And although the reliability indexes are still above the allowable values, it can be considered as a kind of threat to use the structures in the current condition, and really we require maintenance or retrofitting for these structures. We also apply the modular Bayesian model updating approach to update the P block, and we obtain very good result in natural frequencies compared with the measurements. For example, the errors in the first mode reduced significantly from 9% to 2.57%, as well as the error in higher modes reduced from 8.58% to 2.76%. This slide actually shows some one of our recent research study. Our group recently developed damage identification approach for mass vary structures. Okay, so we use model kinetic energies. Most of the existing approaches has been developed without considering mass variations. But in this study, we have developed a new sensitivity equations to locate damage with mass variations, as well as the formulas for damage quantifications. And you can see here, the damage can be well identified. We have 3 damage. We have a scenario with 3 damage locations, and it can be well identified if we know the amount of mass variation. All right. So still, this method has the limitation that we need to know the mass variation before doing the damage detection. So we improve the methods. We improve the quantifications methods for the damage and the mass variations at the same time using the principle of energy balance. So we always have this relationship. Total strand energies is equal to total kinetic energies. which is represented by the equations. So if we know the number of damaged elements, which can be found from the method so in the previous slide, we can have these equations with reduced number of unknown. And by inverse calculations, we can identify both damage and mass variations. For example, if you take a look at this table for the multiple damage, the damage is well quantified as 9.4% and 14% at element 6 and element 11 respectively, as well as the mass variation is well estimated at 6.3% compared with 5% in element 6. Another recent study is the damage detection in hyperbolic cooling towers using vibration characteristic. In this study, we use the largest absolute difference of Morse curvatures to locate the damage locations. For example, we have two damage scenarios here, one around the neck and one in between the neck and the upper part. In both cases, the locations of damage are clearly identified with this approach. This is the location of the damage at in between the neck and the upper part, and this is the prediction of the damage around the neck. The third part in our application study is categorized as structural impact mitigations. So in these categories, we have ongoing research on negative poison ratio materials for vehicular crash mitigations. In Australia, there are about 2,000 vehicular crashes into building a year. So this figure shows a typical crash of a car into a building. So we want to stop this. So our mitigation strategy is to use material technologies. In this project, we will develop and apply novel acoustic composites for surface rendering and embed rubbers or neutrons or acoustic forms in masonry choice. So what is acoustic material? So acoustic materials have a special property called negative Poisson ratio. Normally, if you stress a material vertically, it will become taller and thinner, right? But for acoustic material, it will expand in all directions. It will expand in all directions if you shred it. You can see here when you shred it horizontally, it also expands in vertical directions. So with this property, we expect the material can help increase the absorptions and vibration impact, and therefore the damage impact will be reduced. Our strategy will be developed through experimental testing of the rendered masonry wall with damping materials in the between the wall edges. And this will be for the first time such testing is undertaken. We have been awarded an ARC Discovery Grant and ARC Lab Grant for this testing. The testing includes low, medium, and high velocity impact on the masonry wall and under and to the acoustic rendered masonry wall to study the effectiveness of these materials in the mitigations of car crash. And before the test, we have done some numerical study as shown in these figures. These figures show the impact, the numerical study on the impact. Outcomes of the testing will enable us to check the use of acoustic fabric to prevent penetration of vehicle into the masonry wall and damping at wall edges to mitigate the transmission of vibration to all the part of the building. Again, this project is still undergoing, and we will update more results in futures and some workshop. So thank you for your attention. If you have any questions, you can send email directly to Professor Tommy Chen. Maybe Professor Tommy Chen, you want to finish, give some.
Thank you so much, Roland.
Yeah.
And I think because of the time, so we can't have any questions, but you still, for anyone who would like to ask questions regarding this presentation, you can use Q&A, and then we just try to see whether we can have time to answer your question. Okay, so